know that we only have one block left together? It's sad. Are you hiding, Richard? You get to come back in March, though. The grand finale. So let's open the book on page 109. So we'll continue a little bit more with the multi-level regression. And then we'll switch over to the final topic of multiple imputation. We talked about small cluster sizes before. Now we're going to focus instead of the difficulty of having many potentially random slopes. And you may know then that multi-level regression is a little computationally heavy when you have maximum likelihood estimation you look for several random slopes. The iterations take a long time. When you have categorical dependent variables, you have to rely on numerical integration, and that is heavy as well. So let's see what Bayesian analysis can do in that regard. We have an example here, a simulation study. I'll put it up on the other screen as well. So this is from the Bayesian analysis paper by Tihamer and I, website. And you have, in this case, a simulation study with a random intercept and some random slopes. And we have Q random slope, random here. We have, when we say Q equals 1 in this case, that implies that there's only a random intercept. And then when we add 2, when we have 2, we have random intercept and 1 slope, random intercept and 2 slopes, random intercept and 5 slopes. So that's how it works. So in this case, we have a sizable number of clusters, and each cluster is of a sizable size, 20. So that's not the issue. Sample size is not the issue. But the issue is how well you estimate the random intercept variance, which again is a characteristic of, say, school or classroom heterogeneity. And you may want to divide this table. You may want to draw a vertical line right here between 3 and 4. And say that to the left of the line we have bad results. To the right of the line, we have good results. Just to keep it simple. And why do I say that? Well, the true value of the random intercept variance is 0.5. And here is what is estimated, 0.03, which is not quite 0.05. And 90 in parentheses tells you what the coverage is. That is, we do this simulation study over many replications, and we ask ourselves, which percentage of the times of these replications does the credibility interval cover the value of 0.5? And it should be 95% of the time. So, well, actually, I had it backwards, folks. To the left of the line is good. To the right of the line is bad. You knew that, right? I was on some other page. So what you're looking at to the left here, you're supposed to say, oh, those values all look pretty good, at least in terms of coverage. 90, 89, all right, not perfect, but here it is all right, and here it is all right. You have, actually, it's not the estimated variance component here, it's the bias, as it says in the heading. 0.03 bias is point estimate-wise a little bit off from the true value, but the real focus is the coverage. Coverage is fairly good. But as you go up to higher dimensions, the coverage gets fairly bad. That is Boy, this looks funny, doesn't it? I don't think I know what this table says. Yeah, maybe this is a typo. Maybe you should put this slide aside and let me tell you what it was supposed to say. And this is the feature of live performance here for the first time. So what this is supposed to illustrate is that the random effect estimation gets more and more difficult the more random effects you have. And it's also dependent on the kinds of priors that you put on the random effects. And we have made an improvement actually in Mplus between 6.0, which is out right now, and 6.01, which is coming soon as a minor polishing of version 6. So let's go past this example, and I'll refer you to the paper instead where you can read about it. Let's instead take a look at this situation where you have a small slope variance. So we're still in the situation where we have multi-level modeling and random slopes that we want to estimate. You have in this case, you have a Monte Carlo simulation still, and you have a random intercept and 2 random slopes. It's fairly realistic that you don't have too many slopes that need to be random in multi-level regression. But the second slope is one that has a variance of 0. So you have 2 x variables, and you want to know if both slopes need to be random. You don't know beforehand that it's only one of the slopes that need to be random. What do I mean by random slope? It's a slope that varies in value across the clusters, across the schools, for instance. And you have, again, 200 clusters of size 20. And we're saying here, giving the final outcome of this, Bayes takes only 5 seconds per replications in the Monte Carlo simulation study, whereas ML takes 19 minutes per replication, quite a lot longer time, due to slow convergence that happens when a random slope variance is 0. So ML uses that EM algorithm, and the EM algorithm, even with acceleration of it, is very slow when one of the variances is 0 for the random slopes. And it takes a long time for the program to tell you that there is no variance. So in the Monte Carlo study here, then, we have, hopefully correctly stated, the bias and the percentage coverage for a small random effect variance estimation. And we can focus on the coverage here. This is what we're going to focus on is the variances of the random effects. And we're going to find that here, this is a variance of 0.00 that comes out here. Sorry, this is the bias of 0.00 with fairly poor coverage. Well, I guess the coverage is fairly okay here. Yeah, fairly okay. Once it converges after its 19 minutes per replication. And for Bayes, we get a certain amount of bias here and poor coverage for that particular variance component. But the true variance component is 0, and the bias is not far away from 0. So I would say that this is an acceptable value for Bayes, even though it goes towards a limiting point. So in conclusion, I can say that the ML performance, once it converges, tells you that the variance is small, but in this case, we're looking at side 33 here. This is the variance that's small. But it takes you a long time to get there, and it may never converge in some applications, whereas it goes very quickly in Bayes and tells you that you have a very small value. So there's an advantage in small sample in small variance situation for Bayes as well. Now, if you take a look at a more complicated model here, you have a multiple indicator model again, and we are still in the two-level setting. You have a growth model where you have development of individuals over time, and where you study these individuals within classrooms. This is actually, again, borrowed from the Hopkins study. So there's students within classrooms. Here you have the model Linda looked at, the multiple indicator model for 8 time points with 9 indicators per time point. So again, 72 observed dichotomous indicators. And we have the 8 factors here. So there was 8-dimensional numerical integration for ML when we had single level, when we ignored that the students were sampled within schools. But now we have a 2-level model, so we have variations across individuals and variation across classrooms in this case. So in topic 8 of our course, we actually talk about this kind of model where in the form of having random intercepts here for each of the indicators, modeled their variation and covariation modeled in terms of the between level factors, between level variation in the factors. And then we have a growth model for this over time with intercept, linear slope, quadratic slope for the within level and for the between level. So this is variation across students, and this is variation across classrooms. So if you look at this, you have 2 versions of it. One version without these little residual arrows here, and one version with them in the model. If you don't have, and these little residual arrows are the time-specific, time and item-specific contributions of the classroom variation. So that's time and item-specific classroom variation that's in there. If you didn't have them in there, your number of dimensions would be 2 times t. That is, the number of latent variables that you would have to integrate over in ML would be the 8 plus the 8. The 8 factors on within plus the 8 factors on within, on between rather. So you would have 16 dimensions of integration. 16 dimensions of integration. And if you had the full generality of the model with these time and item specific between level arrows in there, you would have t plus p times t. So you would have the t, the 8 here on within, plus now you have to count every one of these circles. So it's p, in this case it was 9, times t, which is 8. So 9 times 8 is 72, right? Plus t, which is 8. So you would have 80-dimensional integration here if you used ML. So that's kind of extreme, but it is not an extreme application. This you may want to do. This is sort of a multi-level IRT. And I call it 3 or 4 level analysis because in the multi-level literature, you may view this as 4 levels of variation. That is, you have items within time points, several items repeated within repeated time points, within repeated individuals, within repeated classrooms. That's often how these kinds of analysis are portrayed in the multi-level literature. And in Mplus, you break it down to a 2-level analysis, where the repeated items and repeated time is stretched out in one wide observation vector. And what varies on the 2 levels is variation across students and variation across schools. So we have an example, once again, for those of you who remember topic 4, of a doubly multivariate wide format. So in multi-level modeling, this is referred to as either a 3 or 4 level analysis, whereas in Mplus it's a 2-level analysis. So this was, we did this using Bayes on the Hopkins data just to show that it works in practice. And we've also done it on simulated data. So 80 dimensions of integration can be handled in Bayesian framework. All right, now we're ready for the afternoon and multiple imputations. And that has to do with missing data. So this is a nice byproduct, as I said, nice byproduct of the Bayesian analysis. The Bayesian estimation scheme that we implemented. And it's a very practically useful byproduct, the imputation facility. And the story begins as follows on slide 116. You have analysis with missing data. And you want to make the best use of all available data and avoid biases in parameter estimates, standard errors, and test of model fit. And we know then from topic 4 that we have various kinds of missingness, missing completely at random, and we have missing at random, and we have non-ignorable missingness. And most often, I would argue that we are probably in the situation approximately of missing at random, which means that the missingness can be related to observed variables. So for instance, in a longitudinal study, you have people in grade 1 and then people observed again in grade 3, and many have left the study in grade 3, and their missingness may be related to the outcomes that were observed at grade 1. So if they were particularly aggressive, disruptive, maybe they've left the study, and that would be an example of missing at random because the missingness is predicted by by observed variables in the study. So missing at random does not mean the same thing as missing completely at random. It's quite selective missingness. And the maximum likelihood estimation can be done without bias when MAR holds. Then we have non-ignorable missingness, where missingness is related to values that would have been observed. And that is a more difficult situation. And yesterday I gave a reference to a new paper that I'd written on how to do that kind of modeling using various features in Mplus in that paper that looked at the star-D depression study. Now we're going to focus on these two situations, MAR and non-ignorable NMAR. And we're going to do that in the context of Bayesian analysis. We have these two slides. We're going to talk about correlates of missing data. And one way to make this MAR assumption more plausible is to include covariates that actually have an influence on the missing data, that predicts missing data. So MAR is what is assumed in standard software, all kinds of standard software. If you do maximum likelihood estimation, the software is made for correct maximum likelihood estimation under the assumption of MAR. You cannot test for MAR. It's impossible to test if it holds or not. So you try to make it more plausible. The way to make it more plausible is to include covariates or variables that predict missingness, because then you have observed data on those, and less and less of the missingness is predicted by unobserved variables. Now, the problem is that the correlates of missing data may not have a causal role in the model. So that is, they don't influence the dependent variables, they only influence the missingness. So if you include them as covariates in the model, it biases the estimates. because then the regression coefficients for the covariates that have a causal role will be partial regression coefficient, conditional on the other variables that only have a missing data role. So there are two solutions to that on the right screen. One is in the maximum likelihood framework, and the second is in the Bayes framework. And Mplus covers both of these now. So you have in the maximum likelihood framework a possibility to include missing data correlates in the model, not as x variables, but as y variables freely correlated with all other observed variables. And it's done automatically in Mplus when you use the auxiliary M option. And we described that in the topic 4 handout. And there's also a web talk in Camtasia on that on the Mplus website. So that there is a maximum likelihood approach to doing that. But you can also take a Bayesian multiple imputation approach. And that has the advantage that you can work with two different sets of variables. You can use a large set of variables for the imputation model, and then you have you can still do the analysis using only the analysis variables. Whereas here in ML, you have to bring in the extra imputation variables into the model, and that could potentially create difficulties for the estimation of the essential parts of the model. This multiple imputation then is a Bayesian concept, and it's described, for instance, in Joe Schaefer's 1997 multiple imputation book. As a statistician would like to read it. And in the last few months, there was a book written by a psychologist, Craig Enders at ASU, which I think is much more accessible to non-PhD statisticians. And he also refers to a series of articles that have appeared in Psych Methods, for instance, by people like John Graham at Penn State, writing together with Joe Schaefer. But that book, I forget what the editor, rather the publishing company is, but you have the reference at the end. So that's recommended. Now, let me put up these two slides. So Bayesian imputation then, solution number 2 to this issue of trying to come up with analysis that is free of biases with, in the missing data case. We have 3 steps. We estimate a model using Bayes, and then we draw a set of parameter values from the posterior distribution. And for each set of parameter values, we generate missing data according to the model. So this generates one, for each draw of parameter values, we generate one set of data. So imagine that you have done a Bayesian analysis and you get the posterior distribution for all of your parameters. Then you take a random draw from that posterior distribution, sort of a Monte Carlo approach again, for the parameter values. And for that parameter value set, you generate the missing data according to the model. And then you do it over again, say 5 times, that's often recommended. 5 times, go through steps 2 and 3. You've already done step 1, but you go through, you iterate through steps 2 and 3, say 5 times. And you will end up with 5 different data sets where there is no missing data anymore. You filled in the missing values according to this approach. So it starts again with estimating the model as usual using Bayes. You have a posterior distribution then at the end, and then you take a random draw from that for all of the parameters, and given those parameters and given the model, you do random draws of the data according to that model. That gives you one data set. That's how multiple imputation comes about. You do several draws, at least 5 as recommended, because you want to see the natural variation in the missing value. So you don't want to have just one missing value, you want to have several to show the variation, the uncertainty in the estimation of that missing value. That's the key feature of multiple imputation. Now in step 1 you have a choice, the estimating of the model using Bayes. Typically what's done in the literature and in software is to use an H1 model, an unrestricted model. But what's nice about Mplus is that you can also use an H0 model if you have a good model in mind, which is a restricted model then, for instance, a factor model or a growth model or even a latent class model or a two-level model used in step 1. It will still give you parameter estimates and you can still go through steps 2 to 3. So for instance, with a lot of categorical variables that are missing, you could do instead of having a large H1 model with many parameters then, because you have many variables, you could do a latent class model. If you find a well enough fitting latent class model, use that as your imputation model. That works. And we will see research papers along those lines coming out in the near future. Now when it comes, so we're going to make a distinction between H1 and H0 based imputation. When it comes to H1 imputation, that's the Mplus commands data imputation model equals. We have 3 approaches: covariant, model equals covariance, or sequential, or regression. With continuous observed variables, we have covariance being the default. So we take a Bayes estimation from an H1 model and do multiple draws of 2A parameters, 2B missing data generated from those parameters. Think of this as, sometimes in the literature, that's called the EM algorithm approach to filling in missing values. So you estimate an unrestricted mean vector and covariance matrix and get a posterior distribution for that from Bayes, and then you draw your parameter values and you draw your missing data from those parameter values to create the say 5 data sets. When you have categorical observed variables in your set of missingness variables, a better approach is the so-called sequential approach, which was written about by Raghunathan and others from University of Michigan. It's often called chained equations approach. And that is a faster performing and more stable converging procedure when you bring in categorical variables that have missingness. And we have yet another approach called the regression approach that I'm not going to talk about here. But all of this is described in this multiple imputation note on the Mplus website. Now, there's another side product of this, byproduct rather, you have plausible values. And as I said this morning, plausible values is concerning latent variables for which you have missingness for everyone in the sample. And multiple imputation for latent variables then naturally has to come from an H0 imputation, right? You have to have a model which defines latent variables. You can't work with an H1 model, unrestricted model, because an unrestricted model does not define latent variables. So by its very nature, multiple imputations for plausible values is working from an H0 model, a specific model like a factor model or a latent class model. And it's available for both continuous and categorical latent variables. So you can draw continuous values or categorical values. You do this via the data imputation command, which saves 2 data sets. Save equals imp star for .dat saves all observations and latent variables for all imputations. So you will have a imp1, imp2, m3, m4, m5, for instance, for 5 different data sets. So it saves all observations and latent variables for all imputations. Can be used to produce a distribution for each latent variable for each individual. So think about that for a second. Think of a specific latent variable and a specific individual. What you will get for that individual on that, say, factor is a distribution of plausible values for the latent variable over these, say, 5 data sets. And in fact, when you have latent variables, you may want to do, for which you have missingness for everyone, you may want to do more than 5 imputations. So you have you get a distribution for the factor score for that variable. Whereas in regular factor analysis, you get a factor score, which is like the mean of that distribution, and at most you also get a standard error for that factor score, how precise that factor score is estimated. But here, with plausible values via Bayes, you get the whole distribution, which may not be a normal, and in which case you may want to work with the median, for instance, instead. So that's much more information on the individual level for a latent variable. Together with that, you get a data set that you get from plausible equals, which saves for each observation and each latent variable a summary over imputed data sets. Instead of having it for each of the 5 or many imputations, you take, say, the mean across all of them. You can get the mean and the variance and the percentiles here. So a summary, whereas here you get all the details of the distribution. And there are 2 uses of this, and one is when you are really interested in individual scores, which you often are in research, interested in individual scores for latent variables, including categorical latent variables as in mixture modeling. And another is when you have an interest in secondary analysis. So sometimes when you get these large-scale national data sets, they are presented to you in multiple imputation form. So you can get, say, 5 versions of the data, and then you would do a secondary analysis based on that those multiple imputation data sets. Secondary analysis meaning whatever, say, structural equation model you want to do. This has been written about in several articles. For instance, ETS, Bob Mislevy, when he was at ETS, wrote about it in a 1992 Journal of Educational and Behavioral Statistics. So Mislevy 1992 in your reference list is one good reference. And a more applied one is by a current ETS methodologist. What's his name? Davier, Van Davier, is either under V or under D, where he's written a more applied paper about the practical aspects of using plausible values. And again, plausible values was used or is used in what's reported in the newspapers about the nation's progress, reading proficiency in the nation, using the NAEP, National Assessment of Educational Progress, which uses a big mimic model with a lot of binary factor indicators and a lot of covariates influencing the factor or factors. And they give you, they base the report of the performance of kids on the plausible values for those factors in that mimic model. So it is exactly what we're talking about here. And they even produce data sets that people can request for secondary analysis where that factor score is imputed multiple times by this plausible value technique. So that is an interesting concept, and you can try it out for categorical variables. Perhaps you want to do latent class analysis using only the latent class indicators, not the covariates, and then draw plausible values for the categorical latent variable values, and then do C on X based on that in a two-step procedure. That would be one use of it. Now, am I talking about this or?
No.
No, okay.
Here I
All
come.
right, here comes Linda.
All right. Okay, so now we're going to take a look at a few examples of the various ways you can use data imputation in Mplus. And so Bankton mentioned earlier that you can impute the data according to either the H0, an H0 or the H1 model. And so here's an example of where we're going to impute missing data using the H1 model. And when you do it that way, you need to save the data, and then in a subsequent analysis, you could then use the imputed data to estimate the model, the H0 model that you're interested in. So what's new here is data imputation. And you can see we have an impute option. Impute equals y1 dash y4, x1, and x2. And you see we have a C after x1, which indicates that we want that variable to be treated as categorical during the imputation of the data. And you'll notice up in the variable command, we have names equal x1, x2, y1 through y4, and z. And so even though we're imputing only according to these variables, we're not imputing for z, we will save z when we do the saving down here in the save option. So z will be saved. So impute equals gives the variables that you want the missing values to be imputed for. And this doesn't have to be every variable in the analysis. It can just be a subset of the variables. So this just names the variables that you want to impute for, not all the variables in the analysis. And the end data sets option tells you how many data sets that you want us to impute, and the default is 5. So we're saying here we want 10. And the save option says that we want to save these data sets. And for example, we say example ex11.5 imp, and then we say star.dat. So that star will be replaced by the numbers 1 through 10 to name the data set. So it'll be x11.5 imp1.dat, imp2.dat, imp3, etc., up to imp10.dat. And you'll note that in the analysis command, I have type equals basic. When you impute according to the H1 model, you need to say type equals basic in the analysis command. So that's important. But that's all you have to do. And then you will obtain 10 imputed data sets. And let me put the picture over here. And you can use those 10 imputed data sets to estimate the model on the left screen. And so that's just a growth model. We're used to looking at that, where we have the 4 outcome variables, I and S, and then 2 covariates. And then this is how we do the analysis in the second step. So what's important here is that in addition, when we save the 10 imputed data sets, there's also a file saved, and it's called ex11.5 imp, and the asterisk is replaced by the word list.dat. And what that contains is the names of the 10 data sets. So when you say file equals, you use it to give this list.dat file that contains the names of the 10 data sets. And then when we see type equals imputation, which you have to say, then Mplus knows that it goes to that file and finds the name of the first data set and does the analysis, the second data set and does the analysis, etc. So when you have type equals imputation, the file option is used to give the name of the file that contains the data set names. Now, here we have our used variables list, what we're going to use in the analysis. That's not new. And then our model command. And we just simply specify the model on the left screen we have a linear model with time scores 0, 1, 2, and 3, and we regress the two growth factors on x1 and x2. So this is an example of generating data using the H1 model. And when you do that, you have to use type equals basic in the input file, and you want to save the data sets to then to analyze in a subsequent step using type equals imputation. So that's the first thing that we can do. Now we also have a situation that we've discovered that's quite useful, and that's multiple imputation with a categorical outcome in a growth model or in any model with MAR missing data, where you really want to use WLSMV. With WLSMV, the missing data handling in Mplus is not as good as for maximum likelihood. However, you can generate data using type equals or model imputation or data imputation. So you can generate imputed data, and then you can, in a second step, use WLSMV as the estimator. And that gets around the problems with missing data handling for weighted least squares estimation and allows you to use WLSMV or another weighted least squares estimator. And why is that important? Well, it's important because maximum likelihood, like we said, has one dimension of integration for each factor with categorical outcomes. But another reason is that in maximum likelihood estimation with categorical outcomes, it's not easy to specify residual covariances for the factor indicators. In fact, each residual covariance is one dimension of integration. And this is the strength of weighted least squares estimation. It's easy to estimate residual covariances among, for example, the factor indicators. So that's why you might want to do this. So I think I probably said all of this. ML can be intractable with a lot of factors with categorical outcomes, and WLSMV does not handle missing data that well. So then we have what we're going to show here, Bayes multiple imputation followed by weighted least squares estimation. And we're going to look at a simulation for 5 time points, a binary outcome, a linear growth model with 1,000 observations, MAR missingness, and as a function of the first outcome. And we're going to vary the number of imputed data sets that we use from 5 to 50. And we do an H1 imputation using the sequential option, which is used for categorical outcomes. And let me just say something. So this Monte Carlo simulation, we're just summarizing it in a bullet. But in our Monte Carlo simulation facilities, you can generate the kind of missing data that you think you have. So here we're generating MAR missingness, but it's very flexible for generating data with different patterns of missingness or whatever to study the impact of missingness on your analysis. So here are the results of that. And I would imagine this is in one of the papers that you did and all the inputs. Okay, oh, whoops. Okay, so at the bottom here we see the source. And you'll find all of the Monte Carlo inputs and everything else there. So if you read down at so here we have the mean of U1. The first parameter is the mean of the intercept growth factor. The second is the mean of the slope growth factor. The third is the variance of the intercept growth factor. The fourth is the variance of the slope growth factor. And the fifth one are the covariances between them, the intercept and slope growth factors. And so the first parameter, true value, we have down here is 0 for the first one and 0.2 for the second. And the true values in the Monte Carlo study for the other factors are 0.5, 0.5, and 0.3 for the last one. So here, and the second column shows just using regular WLSMV, regular missing data handling. And here is WLSMV using 5 imputed data sets, and then WLSMV using 50 imputed data sets. So like I said, let's just look at the first parameter. It should be 0. So, and then in parentheses is coverage. We know we want that to be 95. So the first parameter with WS, well, let's just look at this column first, at coverage. So we see that we don't have great coverage, certainly not for every parameter using WLSMV. Coverage with 5 imputed data sets looks pretty good. Coverage with 50 imputed data sets, in most cases, looks better, but not necessarily that much better. And the size of the parameter estimates, the first one should be 0. Well, certainly the imputation situations are closer to 0. The second one should be 0.2, 0.2. Is that really right, Bengt?
It shows the bias.
But this is
the bias, not the.
Oh, okay. So these aren't. Okay, these are biases. Excuse me, not parameter estimates. That's not what you said when we talked about it. No, it isn't. We wrote down the population values in that first column. All right. So okay. So they're biases. All right. So we have very little biases here on WLSMV. They're very large for the regular one. So we wouldn't want to do this. This, unfortunately, probably shows that our missing data procedure isn't that great in WLSMV. And the biases don't really become that much smaller between 5 and 50 imputed data sets. And I think, which points to the fact that most people use 5 data sets, and that seems to be sufficient. So it isn't really necessary to use 100. You probably are just making it a lot more difficult for yourself. But anyway, so this, we think, is a way of using WLSMV and having the advantage of good missing data handling. So imputing and using WLSMV. And this is something that just, came up as we've gotten into this new Bayesian world. Now, okay, so just to keep ourselves in a framework here, we were looking at H1 data imputation. Now we're going to look at data imputation according to the H0 model. Okay. So here we have a well, maybe I should put that over here. Okay, so here we have a multiple indicator linear growth model. And so we can generate our data according to this model, so rather than the H1 model. Okay, so here we have the example of the input. And so on this first screen, we show our estimator equals Bayes. And then we have our model command, where we simply describe, using by statements, the model on the left screen and the bar statement. You can see that it's a multiple indicator growth model, so we're specifying measurement and variance across time by the equality constraints on the factor loadings and the thresholds. And then we specify the growth model. Now, in our data imputation command, we're saying that we want to save 20 data sets, and we're also saying that we want to save the special plausible value file. When you say plausible equals, 2 things happen. We save all of the plausible values in each data set, but in addition, we have that special summary data set that Bengt talked about, where over each individual, we give you some summary statistics for their plausible values. I'm not sure what they are, but something probably like mean and variance, and then I think some percentiles. But so we give for each person that. And then we have save equals, and then once again, ex11.6 imp star dot dat. So we just substitute in the numbers 1 through 20. And as I said, we also substitute in the word list. And in that list, we give you the names of the 20 data sets so that you can use that subsequently. Now, in this analysis, we actually did the analysis and the imputation in one step, even though we're saving the data sets, in this type of a situation, you do the analysis you can do the analysis in one step if the data imputation model is the same as the analysis model. So here's using the H0 model. Okay. Another example of how you might use this, and this is in the two-level setting. So in two-level data imputation, sometimes there's a problem if you try to generate according to the H1 model. The H1 model is the totally unrestricted model, so both on the within level and on the between level, you would be estimating all of the means, variances, and covariances on both levels. Well, the means are only on one level, but variances and covariances on both. And on the between level, oftentimes variances are very small. And because of that, it can be difficult to do data imputation with the H1 model for two-level analyses. That's not saying it's not possible. It is possible, and it might work just fine for you in your situation, but it also could cause problems. And if it does, you can generate your data according to a simpler model than you might want to use for data analysis. And let me just show you what I mean by that. So okay, so that's the one we're looking at. So this is actually the model we want to analyze. So you can see it's much more complicated. We've removed, for the data generation, we've removed this whole center part. We just have one factor. So it's a one-factor model on between, whereas here we have three factors and a growth model. So we're simplifying the model on the between level for the sake of data imputation. All right, so that's the model we're going to generate the data from. And on the right screen here, we see that we're estimator equals Bayes. There's nothing really new there. And we see that we specify the data generation model. That's not the model on the left screen. That's the analysis model. So on the within, we have the three factors. And on between, you'll see we only have one factor. So we're simplified that for data imputation. Now you're familiar with the data imputation command, impute equals U11-U33, and with a C in parentheses indicates the data or those variables are to be treated as categorical. And then we say save equals, and once again, now you know exactly what that means. So then we've saved the data sets, and now we have that model, and we can go on and do the analysis, and we're using WLSMV. So this is another example of how we can be helped to use WLSMV and also have good missing data handling. And you can see we've got the same model specified on within as before, but on between we now have this much more complicated model. Latent, multiple indicator growth with factor loadings and thresholds held equal, and then our growth model with the means of the factors fixed at 0 and the growth factor intercept at 0 and the slope free. And here we're holding the residual variances equal with that label of 6. So this is another example of using data imputation with categorical outcomes for the purpose in a second step of using weighted least squares estimation. And as I said, this allows us to sometimes with two-level, you need to use a much simpler model. to generate the data than you actually want for an analysis model, or than the H1 model, which can be difficult for type equals 2 level. And I think that's it for me.
Thank you.
You're welcome.
All right. Can I borrow that for a second?
Sure.
Because there is a something I want to correct on one of these slides. These are fresh slides, so we have no idea how they're going to go. But two things I want to repeat that Linda said. One is that imputation, we talked about two kinds of imputations. We talked about imputations of missing values on observed variables. And Linda says that we found in these studies that she showed that 5 imputations in I keep fading in and out. Does that happen only for me or for you too? Okay, here's the fine now. Okay, 5 imputations is sufficient for filling in data on observed variables that have missing data. 5 imputations was not any worse than 50, she found. And now for imputation that has to do with latent variables, where you have missing for everyone, you better do many more, like maybe 100. So that's, the plausible value version of imputation, where, of course, you use an H0 model. Linda had an H0 model where she had factors with multiple indicators and also growth factors. So she had a bunch of latent variables that she imputed from. Then once you have imputed the data, if you do it in 2 steps, you can then, in the second step, estimate the model that you're interested in. The data no longer have any missingness. And to say that you have multiply imputed data to be analyzed, you say in the data command, right? Type equals imputation. The question then comes up of how do you test the model fit when you have, say, 5 data sets? And that's what this slide section starting on 141 talks about. And this refers to a paper which we have categorized within technical appendices. So it sits on the technical appendix page on the Mplus website. And I just want to tell you a few things about this. And you have the slide 142, 143 here. And we'll just take a few minutes, we have the time, to look at the formulas and also make some corrections that you can take home. So we have a capital M stands for the number of data sets. So that's the typical notation in multiple imputation literature. And M is typically equals to 5. So let's say we have 5 data sets. And then we can compute the likelihood ratio chi-square test statistic for each of those imputed data sets. And that's called Tm, the test statistic, the chi-square value for imputed value lowercase m, imputed data set rather, lowercase m. And you can create then an average chi-square T bar, right, for across those data sets. Now, you should not use that T bar as a test of your model fit. We will call that the naive chi-square. You may think that the average chi-square is a good way to assess model fit, but it isn't. Instead, we're going to work with a better one, which is called T-imp. T-imp is what you should use. And that comes out of Mplus. So how does that come about? Well, what you do is consider QM here. It's the parameter estimate for the mth imputed data set under your model, say a growth model. And you take the average of those parameter estimates under your growth model, and that will create Q0 bar, which is the average parameter estimates. It's a whole set of estimates from that growth model. And then you do the unrestricted H1 model parameter estimates and take the average of those over the 5 multiple imputation data sets. Then you create something called, here's our first correction, TM. I should say TM with a prime up there, T prime. T prime M, namely the same thing as here. It is the likelihood ratio chi-square test statistic when you fix the estimates at the average H0 estimates for H0 and the average H1 estimates for H1, average over the 5 data sets. So that's a separate run that you would have to do, but that's done internally on Mplus. You fix the parameter estimates at the averages over the multiply imputed data sets for the H0 and H1 model and create that likelihood ratio chi-square test statistic for each replication, each of the 5 replications. And then you take the average of that to get the T prime bar. The bar is the average. Now, T imp then is equal to, T imp is equal to T prime, it should be T prime bar here, same thing as up here. So it should be a bar above there. T prime bar divided by it's a correction factor, 1 plus R3. And as we all know, R3 is equal to, no, I'm kidding, is equal to this expression here. It's equal to this expression where for both of these T's, there should be a bar on top of them. So the correction factor has to do with the T bar, the naive chi-square over on the left, and T prime bar, this peculiar chi-square, which draws on using average parameter estimates for the 2 competing models. So all in all, this is the right chi-square to be using for testing the model fit, and this is the naive wrong chi-square. I think I got that right, but I'm, my confidence is shaky now. So let's see, if I dare to look at this simulation study and find my way through it. There are 2 aspects to a model test. First of all, the model test should have good type 1 error, and second, it should have good power. Good type 1 error implies that it should not reject a correct model. It should only reject the correct model 5% of the time on the 5% level. So it should have a 5% type 1 error, and power means that it should reject an incorrect model. So on the left you have type 1 error, on the right you have power. So here on the left, then T bar, you probably don't remember, but you can write on top of it, that's the naive or incorrect chi-square, where you take the average of the chi-square for each imputation. T imp is the good one. We do this for a model with 8 degrees of freedom, a model with 8 degrees of freedom. So we expect chi-square to be what? 8. The mean of chi-square is equal to the degrees of freedom, right? So we expect chi-square to be 8, and we expect it to be rejected 5% of the time because it is a correct model on the left because we study type 1 error. And then we vary. We have 25% missingness and 40% missingness. Because remember, we're still talking about missing data and analyzing multiply imputed data. It's a lot of new stuff, I know. I cannot keep track of it. So you have then here, say, for 500 observations with 25% missingness. The naive chi-square average is 16. It's twice too high. And you reject 45% of the time, even though the model is correct. And you should only reject 5% of the time. So the naive chi-square is too pessimistic. So if you've been doing naive chi-square, now you are in a good place. You can go home and get well-fitting models. The correct chi-square that handles the imputation data correctly has an average that's much closer to 8 and a rejection frequency that's much closer to 0.05. and it goes towards the right level when the sample size gets to be 1,000, whereas the naive chi-square does not improve at all. So that's pretty nice, right? 40% missing, even worse for the naive, and still quite okay for the imputation corrected chi-square, except it doesn't perform that well for sample size 100, but then again, if 40% is missing, you only have 60 observations. So that's type 1 error. Naive does poorly, the right one does well. Power, what about that? Well, for power, we have now the possibility of comparing Bayesian multiple imputation and ML. That is, if you have missing data, you could do a maximum likelihood estimation, right? Under MAR. You can even do that with respect to missing on X. As we've said before, you can bring in the X's into the model and make a normality assumption on them, for instance, and do a maximum likelihood estimation, sometimes called FIML for some unknown reason, full information maximum likelihood. I would just call it maximum likelihood with missing data. So when you have missing data, you have the alternative of doing ML under MAR, or imputing by multiple imputation and then doing analysis of the non-missing data. So we compare the two here in the 25% missing case and the 40% missing case, and we're looking at percentage rejection rate here. So let's take, say, out here, 300 observations. The model is incorrect here, so we want to have a high rejection percentage, and it's 92 for FIML, for the maximum likelihood approach, the direct approach, the one-step approach, and 85% rejection for the two-step approach of first generating multiply imputed data and then analyzing them. In this case, analyzing them by ML. So that's not too bad for the imputation. It's fairly close to 92, and at least it is a decent power for 300. But when you go down in sample size here, the imputation power is less, and the difference becomes bigger between the direct ML and the imputation. So when you have small sample sizes, say less than 250 or 300, you may want to try to stay with the full information maximum likelihood. That's what this slide says. And with that, we switch over to, we leave the Bayesian arena. I just want to say one final word about the Bayesian. I hope we could stimulate your interest in it by examples like the Bayesian CFA. I think that is a pretty compelling example of the potential for Bayes to have these informative priors on the cross-loadings that not only makes for a very relevant reflection of the substantive theory, but also makes the model then fit or not be rejected needlessly, and also provides modification indices. In addition to that, new research in the last in the last week or two points to the fact that you can generalize that idea, and you will see that shortly in writing, to factor analysis where you let the residual correlations among your factor indicators correlate but have small variance priors placed on them. So imagine that your theory is that you have big five theory of personality, for instance, has 5 factors, but you really have a whole lot more factors than 5, very minor factors that create residual covariances among your indicators beyond what the big five factors can explain. Well, you can let all of those residual correlations be free. They're not identified in ML, but in Bayes, you can put small variance priors on those correlations with mean 0, essentially, but a little wiggle room. And therefore, the model is estimable and will be a much better reflection of a substantive theory than a standard factor analysis, which assumes that there are no residual correlations. And that seems to be a very promising approach to not needlessly reject models that are otherwise good. So I'll leave you with that tantalizing news.
And also, before you turn off your microphone, I thought of two things that we didn't say, and then you might want to say something about them. And that's that when you say type equals imputation, you not only get this special chi-square, but we average the parameter estimates over imputations as is correct, but we also give correct standard errors. We don't just average the standard errors over imputations. And I thought that's according to the Rubin formula.
Right, that's a good reminder. So the standard errors are computed according to this so-called Rubin formula, which takes into account variation, the standard error for each imputation, but also the variation in parameter estimates across imputations. So it's sort of a within-between variance that's taken into account to get the right kinds of standard errors.
Right, we didn't even think about that.
That's right.
Okay, so now we want to just give a brief overview of other new features in version 6. We won't discuss them in detail, but just let you know, in case you don't know, what you might be interested in trying out. So we have, this is an interesting, a lot of times these new options become available because of our own needs. And so finally, Bengt wanted to have starting values as part of the input statements. So you can use the S-values option in the output command. And if you do that and you run an analysis, then right after the analysis, you'll receive all of your input statements, but they'll each have asterisk starting value, and the starting value is the ending value of your analysis. When a model doesn't converge, we automatically give that now. So that a person, when we give the little message saying you might want to try starting values, well, now you can just copy and paste and start and do that. There's a couple, we don't give them for the bar statements, so you need to kind of compare your input to the new input with starting values and make sure you don't leave out any statements. And then we also have had a need to do some really minor merging of data sets. I mean, this isn't like merging all of SAS or anything, but you can take two data sets and have them merged on an ID number or something like that, and that's part of the save data command. People have requested for a long time for 90% confidence intervals. We give 95 and 99. So now we give 90, 95, and 99. So for those of you who wanted that, you got it. And actually, I think this is true. C-intervals works for Bayes, right? But we just happen to give the credibility intervals as part of the output for the 95%. Right. Yeah. So the C-intervals option, we give the 95% credibility interval as part of the results for Bayesian analysis. But if you happen to want 90 and 99 and 95, you can use the C-intervals option with estimator equals Bayes. Then another thing that we've been giving univariate frequencies for categorical variables over the years, but we give error messages telling you have a 0 cell in your bivariate tables. But of course, we don't give you the bivariate tables or a way of looking at them. So now we do. We have a crosstabs option, and this is also in the output command. And that's for binary ordered categorical and unordered categorical nominal variables. And another thing that we've done in the graph is a lot of times people save they have settings they like, but then once you leave, you lose your settings. You have to put them in when you come back. So now that's not the case anymore. Under Axis Properties, as part of the graph menu, you'll be able to save the settings. And then this is a pretty big one. We have added for frequentist factor scores, standard errors in most cases. So when you save the factor scores, the standard error will be saved next to the factor score. Now, in all of the estimators that end in MV, WLS MV, ULS MV, and MLMV, as you all probably know, the only value that you were able to really use from that was the p-value, because the chi-square and degrees of freedom were adjusted for those estimators to give a correct p-value. And that has been distressing to people because their degrees of freedom weren't correct, or weren't what they expected. I can't say they weren't correct. But anyway, so what we've done is Tiamir has developed a new adjustment along with Banked. And so now in WLSMV and the other MVs, you will see the usual degrees of freedom that you would see if you did, for example, WLS. So there's a new adjustment there. Now, in survival analysis, we've added quite a few things, actually, and we'll come to the plots later. But as part of this paper that Bank did in connection with the Eli Lilly collaboration, a need came up to have a survival intercept that could capture treatment and control differences. And so for continuous time survival, we have added the ability to access a new parameter in the model command. So that's something that you might find of interest if you're a survival analysis person. And then we've added a lot of survival plots for both discrete time survival and continuous time survival. Now, for discrete time survival, you have to use the desurvival option of the variable command. Unfortunately, as I was writing the user's guide, nobody told me about this option, even though I asked many times, have I missed any options? But anyway, so lo and behold, no, it wasn't you. You're innocent in this one. Lucky you. But the first email I got about version 6, believe it or not, was somebody saying, I want to do the survival plots that I'm doing discrete time survival, and they're not coming out. And so I said, well, wait a minute. I asked everybody, why aren't they coming out? And they go, oh, we didn't tell you. So anyway, this is not in the user's guide, but if you have discrete time survival, you say desurvival equals, and you just give your outcome variables. And you do this in the variable command. And if you do that, or if you have continuous time survival, where we can tell that you're doing survival by the time-censored option, you're going to get Kaplan-Meier curve, sample log cumulative hazard curve, estimated baseline hazard curve, estimated baseline survival curve, and estimated long cumulative baseline curve. So we added those. This was all part of that collaborative project where, we really developed continuous time survival analysis a bit more. Now, another new thing that a lot of people may find interesting is we added a data missing command. And this came about because of the collaboration on the STAR-D antidepressant trial work, and where missing data was taken into consideration, non-ignorable missing data. So what data missing does is it creates missing data dropout indicators for non-ignorable missing data modeling of longitudinal data. So you have type equals S dropout, which is like a survival dropout dummy set, and that's used for the Diggle-Kenward selection modeling. And then we have type equals D dropout, which are just dummy dropout variables that you can use for pattern mixture modeling. And we've given a fuller set of descriptive statistics for dropout to help you better understand what your dropout looks like. And we have plots of sample means added for before people do drop out. So that's that. Oh, I'm sort of like reliving version 6 here. Oh, we did that too? It seems like a lot. So anyway, we added replicate weights. A lot of people, now have complex survey data sets where they are provided with replicate weights because this is a way of protecting people's identities. And so all of the information about the sampling design gets put into the replicate weights. And then, but you need to actually be able to use the replicate weights appropriately. So that's available now in version 6. And we also added a finite population correction factor for type equals complex. Some other complex survey data features is that the Pearson and log likelihood frequency table chi-square are now adjusted for non-independence for type equals complex, which is data that aren't independent, and for models with weights. And once again, here's a paper that discusses that. It's a technical appendix on the website. And also standardized values in Tech 10. Tech 10, we've talked a lot about it, the univariate, bivariate, and response pattern residuals. So the Tech 10 values are now adjusted for type equals complex models with weights. So before those, they were not corrected for that. So they are now. So we added quite a few new complex survey data features. And here are the references that were referred to, the multiple imputation reference, Bayesian analysis, and all the other, and exploratory structural equation modeling, which wasn't actually added in version 6, but it only got into the user's guide in version 6. It was only in the addendums up to then. So do you have any? Well, we should take questions, but you should say what you want to say first.
Thank you. So just to add a few things there, we're supposed to stand here to be lit properly. Just to add a few things, the examples that Linda went through on multiple imputation are covered in User's Guide Chapter 11. So you have a little bit more text explaining the setup for those examples. And also, when Linda mentioned the new missing data descriptive features, the S dropout and D dropout and Diggle-Kenward and pattern mixture, those are also have examples in the User's Guide Chapter 11, the new Chapter 11. And anyway, those techniques are described in that NMAR paper, non-ignorable missing data paper on the STAR-D data set. So you can read more about it. I thought I could just take a few minutes to talk through various kinds of references on Bayesian analysis that you might be interested in, and point out those that are perhaps particularly accessible or relatively so. Here are clearly technical. The first two are technical, and only for the tech nerds would I recommend them. Here, although good papers, here is the Brown and Draper, nice overview O2 level simulations, trying to figure out how various kinds of variance priors work for two-level data with a small number of clusters. Here is an attempt in the American Statistician, an early one from '92 by Casella and George, explaining the Gibbs sampler. Gibbs sampler is a form of Markov chain Monte Carlo simulation method. Here is a very interesting paper by a Swedish team on random change point modeling for assessing variability in repeated measures of cognitive function. So that has to do with the cognitive drop before death and estimating that change point. And it's done by Bayesian analysis, a nice application-oriented paper in statistics in medicine. We don't yet have the explicit capability to do this in Mplus, even though we have Bayes, but now we have the Bayesian platform for developing the capability in the near future. Let's see, here is Craig Ender's Applied Missing Data book, the new one. So it's a Guilford book. Here you have Bayesian estimation techniques described for multi-level IRT models using Gibbs sampling. Again, whenever you see Gibbs, you should just think Bayesian analysis. In Psychometrica, so it's by its very nature a little bit technical. Let's see. Here in Gelman et al., 2008, you can read about weakly informative default prior distribution for logistic and other regression models. Why would you care? because totally diffuse and uninformative priors is not the best choice when it comes to loadings for categorical factor indicators or categorical indicators of in an IRT model. They are too diffuse. You may instead have a weakly informative prior, sort of an in-between, where it says that your loading is not average 0 and the variance infinity, but your loading has a little smaller variance. You expect the loading values, for instance, to not go beyond 5, plus minus 5, and even you can even put a positive prior on it. And that just mildly informative prior improves estimation quite a lot for categorical dependent variable slopes. Let's see. Here's the book that I recommend for those who are statistically oriented. I've learned a lot from, and can learn much more, from this Gelman book, 2004. Here's the Gelman, Meng, Stern, Rubin seminal paper on the PPC, posterior predictive checks, in Statistica Sinica. Here's an example of image analysis using MCMC from a Richardson Spiegelhalter edited book on MCMC, a classic book in the Bayesian analysis. Image analysis is an example where ML would have a very hard time. That is trying to reproduce images statistically. ML would have a hard time, and Bayes is called upon. Let's see. What's of interest here? Here is a book on structural equation modeling using a Bayesian approach by Si-Kyung Lee, a Wiley book. It's technically oriented, but it is a good resource book for those who can read that. Here is a book that I sort of like in terms of those who call themselves introductory statistics books for Bayesians. This is probably one of the better ones, I think. It's not introductory enough. But among the ones who try to be introductory, I think this one has succeeded to a much larger extent than others. Lynch has written a good thing for social scientists. So it contains a lot of accessible technical matters. Here is the MBR paper we referred to. Let's see, what else is Bayesian here? We have a lot that we know about. Here is more on Bayes for IRT model by Patz and Junker. Here is the Raghunathan et al. Paper we referred to for, this is almost like the credits in the movie. Don't you get that feeling? I certainly got that feeling. Boy, this is recorded. This is the sequential method that we talked about as an H1 imputation technique. Survey methodology, and Don Rubin's multiple imputation book, quite technical, but of course very good, written by Don. And here you can ponder to Bayes or not to Bayes, and moving from the state of whether to when. And that's in structural equation modeling with applications in it. Schaefer's book here. And here's a psychometrica paper, early psychometrica paper, early in the MCMC world. On this is the PPP method using chi-square that I talked about. It's used in that paper as well. Here is Aisuke Sugawa in the Chicago area, where in JEBS he looks at a Bayes estimation of generalized linear model. That means that it's for categorical dependent variables. Let's see, here's the Spiegelhalter article, actually about the bugs reference. And here's the Spiegelhalter et al. Paper in JRSSB where they talk about the DIC and have a discussion about that. People who are pro and con that. And apparently Bayesian analysis has to do with semi-parametric modeling, which is almost like non-parametric modeling of structural equation models. So you see more and more Bayesian papers related to latent variable models. And here is the 2009 paper that Linda talked about, the second path analysis example. And I had the note that that's a nice Bayesian introductory article as well. I think there's a need for even more introductory, as I said, but that's a good attempt. And that's the one that has the Winbugs code in it as well. And I do believe that slide 163 is the last one. And that's where the lights went out. So let's see. I think we can. 3 o'clock. Who knew? Ah.
Oh, but we haven't done questions and answers yet. So it could be after 3 then.
All right. So where do we want to be here? So, okay, now it's your turn. You can ask us questions until our plane leaves. But please don't. Yes?
I had a question about slide 123 and 127.
123.
This is where you indicate that you can model X1 as treated as a categorical imputation process, but then in 127 you indicate sequential. So I assume that since you didn't indicate sequential in 123, then that would be analyzed as multivariate normal, and I'm missing something.
No, that's exactly right. So here on 123, which is example 11.5 from the new user's guide, the variables are all treated as, well, actually here, in 123, right. Since we have one variable declared as categorical, it falls into the default of the sequential method there.
So right, the defaults aren't the same always in all situations.
And you will see what has been done in the summary in the Mplus output. It will tell you what the imputation method it actually used. By the way, it will also tell you now, if not now, then in 6.01, what the priors are for each parameter would actually be printed. The priors that were used by default or by your specification will be printed at the end of the Tech 1.
That's in 6.01.
Yes?
It seems like I'm just wondering, is Z part of the imputation model or just variable that is saved?
So could you say that again? Which slide are you on?
Same slide.
Same slide.
The last variable Z, is that part of the imputation model? And the variable
Oh, Z. Z.
Only the variables on the impute list are part of the imputation model.
So this variable, I assume this variable will be transferred over to the imputed data set?
That variable will be saved, but it's not used for imputation. Only what's actually on the imputation list. So that's what I'm saying is, like, let's say your analysis variables are Y1 through Y15. If you only have impute equals Y1 and Y3, that's the only variables for which data will be imputed. Just the regular values will be in every data set for all the other variables. Is that correct, Bengt?
Mm-hmm.
Right.
Debbie.
Sometimes when we're doing imputations, like in SAS, we set like minimum, maximum because things that are positively skewed, sometimes it's hard to estimate that. Is there any mechanism to do that in Mplus, or just because sometimes like it'll give us a negative value for something that has the positive skew?
We have that feature for the categorical variables that you could limit the number of the categories that you want to have imputed. But I don't think we have. I don't think we have it for continuous variables to limit the range of it. That may be something we need to add as the need arises. Yes. Yes.
Is there any option to specify that your data is missing monotone or not, just to speed up the process of imputing?
So the question is there any way to tell the program that the data are missing in a monotone fashion or not? Monotone meaning a typical example would be dropouts. If you're missing at time point 2, you will be missing at time point 3, 4, and 5 as well. No, there's no option of saying that. And I don't know that the computations are pretty quick anyway, so we haven't seen a great need for doing simplifications based on that. Yes?
H0 restricted model is something that's not currently available with Bayesian analysis, so something with censored outcomes or multiple categorical named variables. Can you still use this imputation approach using the H1 unrestricted model?
So the question is, what if there is a kind of analysis that can't be done in Bayes currently, like censored, normal, or count variable analysis? Can you still do imputation using Bayes, and then for the imputed data, do maximum likelihood estimation, which does censored, normal, or count? All right, that's a good question.
But we don't impute. Don't we only impute for continuous and categorical?
Right.
Yeah, so
That's a good answer.
we don't impute for those other variable types. We only impute for continuous and categorical.
So I wonder, though, if you could... so it wouldn't be exactly right in the imputation stage. So I do think we have to wait for that further development.
We'll tell Tiamir when we go home.
Yes, gentleman in the back.
He is.
Is there a provision to restrict it? For example, if you have legitimately missing data that you do not want imputed, say months since stopped smoking, and you don't want to impute that for people who have never smoked, is there a way to do that? Or if you're doing a two-stage imputation of a semi-continuous variable?
Right. Yeah, so you would just change, you would just declare that as an okay value and not declare it as a missing value. So you're excluding that variable from imputation. So essentially, you don't have to impute all variables. Some missingness you may want to treat in the subsequent analysis.
No, but what I'm saying is, if some of your participants, you want to impute that data because they're missing and they should have had values there, but some people are missing because they didn't answer that question because it was not clear.
I see. So you have like two groups of individuals. One for whom you don't want to do any imputation because the value is not relevant.
For example, one person said they had no children, so they're not going to answer what are the ages of your children items. Somebody else said they have kids but didn't tell you the ages.
Right. But couldn't you just so you don't impute for that person? Why don't you just not say that there's missingness on that, or give it another designation?
Exactly.
The data doesn't exist, but you also don't want to designate it as missing, say, 999 here to be imputed. Wouldn't that work? Right. Right. So you can call it 998, and then when you go to analyze the data, 998 means missingness. But for those that you wanted to impute, to say 999, and you get imputation for them.
So we're going to impute for anything that has a missing value flag declared during imputation. But you can alter your missing value flags such that all of them don't get imputed for.
So for some individuals in your sample, you change the missing data flag. You don't declare it as missing. Yes, Debbie.
So will Mplus use the variables to estimate the missing values if they're in the variable names list, or it needs to be in the impute list? So for example, if I'm missing a lab task, but I have other indicators of the latent construct, which I have full data, and I want to use the other indicators to help me estimate the lab task missing data, would I put that in impute, or would it be used if it's just in the variable names?
The variables that you want to, well, do you want to answer that?
I didn't really understand it.
Okay, sorry. So say I have missing on a lab task that I want to estimate, and then I have two other measures for which I have full data that will help me estimate those missing data points. Where would that go? Would I put that in the impute statement?
I think if you, that's I think the beauty of this is that you can have more variables on the impute list to help in the imputation of the data than you may want to use in the analysis. That's like the missing data correlate idea, right?
Yeah. So you would put, so this is the step where you just do the imputation, and then you do analysis. You just put them on the impute list here.
Yeah.
Yes, Richard.
Question, sir. If you running an analysis involving Bayes estimation and don't, the default assumption with missing data is to use the maximum likelihood estimates. Is that true?
The default assumption for actually doing the analysis based on the...
You're running a job with Bayes estimation and the missing data, and if the default is to use the maximum likelihood estimation algorithm for missing data?
As the second step?
Yeah. No.
Okay,
I'm running a job with Bayes, latent class analysis, estimation Bayes. I have missing data on some of the variables.
right.
How does it get an estimate of the missing data? Is that
Yeah, no. So if you have a specific H0 model, say a factor model or latent class model, and you say estimator equals Bayes, then it will estimate the model parameters according to Bayes, and if you request data imputation, it will create an imputed data set based on the Bayes analysis. It's a Bayesian imputation.
What if I don't ask for imputation?
Then it'll just do the model estimation using Bayesian estimation.
Then it will just estimate your parameters directly, pretty much like ML does.
Okay.
So ML and Bayes are very similar. We should make that statement. I'm glad you asked. ML and Bayes are very similar when it comes to missing data, particularly MAR. If you consider MAR missingness, both Bayes and ML estimators use all available data and estimates the parameters of the model. They don't do it the same way, but you get essentially the same results when the samples are large and you don't have, and you have non-informative Bayesian priors. So it's not like, so Bayes doesn't have to impute and then analyze. In a sense, it imputes as it goes along for the missing values, but it focuses on estimating the parameters. So what you should expect if MAR holds, or if you use the same variables in the Bayes and ML analysis, if you have reasonably large samples, that the two procedures should give similar results. It's just that sometimes it's harder to do it in ML, and sometimes it's advantageous to do multiple imputation in Bayes because you can have a larger set of imputation variables. Good. All right, more questions, folks? It's only 3:15. Who can ask one more question?
Don't force them.
Yes.
You suggested that as estimates of the parameters that in a posterior distribution, we might use the median instead of the mean. But we report the confidence intervals in terms of the mean. Does it make sense that we could also take some analog, some variation of the median, and using that report some 95% coverage based on the median and its variation as opposed to reverting back to the mean?
Well, it's good to revisit that. So the credibility intervals that are created in Bayes are not based on the mean or median. It's based on the percentiles of the posterior distribution. So they are totally free of dependence on mean or median or mode. They just sort the data from lowest parameter estimate value to the highest and figures out the 2.5 percentile and then 97.5 percentile in that empirical distribution. And that's just what you want. But that's good to hone in on that and emphasize that. Well, folks, you've been very good, and I'm glad you came here for your Bayes day, topic 9. And now you can go home and consider when and if you want to get into Bayesian analysis as a complement to your frequentist endeavors. So good luck with that.
Thanks a lot.
And again, we want to thank